Hello, everyone. This week we're going to be starting chapter 20 over magnetism. We just wrapped up our unit over electricity. So today I want to dive right into discussing in a little more detail some conceptual properties of magnets before we get into the math. And so one of the most important properties of magnets is every magnet is a dipole. Analogous to how we have positive charges and negative charges, and how those like charges repelled one another, and opposite charges attracted one another, we have a similar scenario with magnetism. So every magnet itself is a dipole. So if you have two magnets and you bring their north poles together, then there is a repulsive force between them. Similarly, if you bring their south poles together, there's a repulsive force. However, if you bring the opposite poles together, there's an attractive force. And so I borrowed a couple of strong magnets from lab, and so I just wanted to demonstrate this really quickly and kind of give you an idea. These are neodymium magnets, and these are pretty strong magnets. So as you can see, I smashed my fingers a few times with these as well. So this bigger cylinder magnet is a little stronger. The smaller cylinder is made up of individual magnets, but when these magnets are attached together, you see that, they act as one. So this whole magnet has a north pole and a south pole. Okay, if I split these up, and these are really hard to get apart, so and I break one of the magnets off, I free it from the rest, then this part that I broke off now has a north pole and a south pole. It is still a dipole. Okay, and likewise the remaining magnet still has a north pole and a south pole. And this is an important property of magnets. You can break a magnet down into smaller and smaller pieces, and each component piece will still have a north pole and a south pole. So these are really strong. So right now I'm holding like poles together. So if I move these closer and closer, I can get about that far apart, and I can't force them to go any closer, right? However, if I turn opposite poles, if I turn them both over, then I have like poles on the other side, and again, they're repulsive. However, if I flip one so that we have a north pole and a south pole facing one another, then when I come within a distance where the attractive force is greater than the frictional force and the weight of the magnet holding it to the table, then you can see that they are very much attracted. Now, trick I like to do, if I place this magnets such that like poles are facing one another, right? Then the magnet will continually orient itself so that the opposite pole is facing the opposite pole of the larger magnet, right? So again, these are really strong. So that gives you a little real life demonstration to break up the monotony, hopefully. So for this demonstration, I wanted to show you how to make a homemade compass using just things that you find around your yard and your house. So here I have just a bowl of water. Here I have a regular sewing needle. It's metallic. You can see that. And here I have just a leaf. So I have downloaded just a simple compass app because I didn't have a compass here at my home. And just to verify which direction is north. So north is approximately this direction, okay? So if you can see the top of that needle there, that direction is north. So next I'm going to magnetize my needle. So magnetism can be induced in metallic objects. That's because when you bring a magnet close to a ferromagnetic object, there is an alignment of electron spin states within the metal in the needle, okay? So this means that the needle becomes temporarily magnetized. Now, eventually it will go back to random states, which we'll talk more about in a later video. But also note what is happening to the compass as I bring this strong magnet near, right? So the magnet has a magnetic field, which affects the compass needle, right? So I'm going to put my magnet back out of the way. Right, and we are back pretty much on north now. Okay. Okay. So as you can see, the red needle is pointed approximately north. So now I'm going to take my needle and just kind of thread it through the leaf. And then I'm just going to place it on the water so that the needle is the tip of the needle is pointing to the left. And so what happens is the needle sends. Okay. So we have our homemade compass. Let's test it again. So again, it will always orient itself back. And let's see what happens when we turn it so that the opposite pole is facing north. So again, just like we saw with the cylinder magnets earlier, the magnetized needle its pole will always, the same pole will always point northward, right? So I hope you've enjoyed these demos.